Okay, for sketching a curve, there are certain things that we want to see on the curve. The first several things that we are going to find are not using calculus. They're things that we already know how to do using algebra. So if I give you a function, the first thing I want you to do is find the domain. And we saw that sometimes we get a critical point that is not in the domain. So we need to know that before we start. Now, if we have a rational function, if we look at the domain and it doesn't cancel with anything, then we have a vertical asymptote, right? If it simplifies out, then we have a hole. We're not going to get holes today. So I want to find the domain, and then I want to use that to find the vertical asymptotes. Well, if there are any, I also want to find the horizontal asymptotes. I also want to make sure when I sketch my graph, I cross the x and the y axes in the right place. So I want to find the intercepts. And I get those where x equals 0, that would be the y-intercept, and where y equals 0, those would give me x-intercepts. And then finally, we're going to use some calculus and find the relative extrema and the points of inflection. So we're going to put all of this together. All right, so we're going to sketch the graph of 2x squared over x squared plus 2. So the first thing I want to know is what is the domain of this function? Okay, so domain, we look for two restrictions. If there's a square root, we want to make sure we're not square rooting a negative number. We don't have any square roots, so that's not our issue here. But it's a rational function, and we want to make sure the denominator cannot equal 0. So normally I'd say, okay, let's set the denominator equal to 0 and solve. But I'm looking at this and I'm thinking, if I take a number and I square it, I'm going to get a positive number, right? And then I add 2 to it. Am I ever going to get 0? No. My domain is all real numbers. Which means I do not have any vertical asymptotes. Now let's find the horizontal asymptotes. We get the horizontal asymptotes by taking the limit as x goes to infinity of our function, and also as x goes to negative infinity. In that in this particular instance, this particular function, whether I do positive infinity or negative infinity, I'm going to get the same result because I'm squaring the x values. So the negative infinity is going to give a positive infinity. So when I look at this, I see the 2 is insignificant. Then I have x squared over x squared will go to 1. So this limit is 2. So my horizontal asymptote occurs at y equals 2. And that's occurring going both to positive infinity and negative infinity, because if I took the limit as x goes to negative infinity, I'd have the same result. Okay, then I want to find the intercepts. Okay, so the first intercept would be the y-intercept. It's the easier one to find, so I'm going to do it first. I evaluate the function when x equals 0. That gives me the y-intercept. Well, when x equals 0, so I'm plugging that in over here, what do I get? No, I get 0 over 2.
I thought you just meant the denominator.
The way I just highlighted, I can see that. I get 0. Okay, now, if it goes through 0, 0, that's not just the y-intercept, that's the x-intercept as well. But that doesn't mean that I don't have other x-intercepts, right? We can only have one y-intercept if it's a function, right? We can only have one point on the y-axis, but I can have multiple intercepts on the x. So we need to check. X-intercepts occur when y equals 0. So if I set the function equal to 0, then if I multiply both sides by the denominator, zero times whatever just gives me 0. So I get 0 equals 2x squared divided by 2, which is just going to go away, right? So I get x equals 0. I got the same intercept that I had already found because 0, 0 is an intercept for both x and y. Okay, so that's going to be the only intercept that I have on my graph. So the information I have right now is that I have a horizontal asymptote at y equals 2, and my graph is going to go through the point 0, 0. Now it's time to do some calculus.
Wait, before you go,
All right, so we want to take a derivative so we can find our critical points, which are our possible maxes and mins. So this is going to be a quotient rule. And I have low, D high. D high is going to be 4x minus high. D low will be 2x over low squared. So let's clean up our numerator here. If I distribute that 4x, I'm going to get 4x cubed plus 8x minus 4x cubed all over low squared. And 4x cubed minus 4x cubed goes to 0, so we just get 8x over x squared plus 2 squared. So our critical values, our critical numbers occur when either my derivative equals 0 or is undefined. So my first critical number is going to come from setting the numerator equal to 0, which gives me an x value of what?
0.
Okay, so we're going to get x equals 0. Now, same as when we found the domain, I've pretty much got the same denominator, but I've squared it. Is anything going to make that denominator equal 0? No. I'm not going to be able to get a real number that makes that denominator equal 0, so my only critical number is x equals 0. So that is a possible extrema, and it's the only one. Now I'm going to save the first derivative test and wait until I do the second derivative, and we're going to put it all in one big number line and do it all together. So now I need the second derivative. So the reminder here, my first derivative we just found is 8x over x squared plus 2 squared. So we're going to use quotient rule. And I want you to think about this. Anytime you use the quotient rule, we think about how many terms are in the denominator. Is it going to simplify in the end? So I have now this whole quantity squared in the denominator. Technically, that's a single term. We're not going to work the quotient rule any differently. It's just that it's going to simplify. So my second derivative is low. D high would be 8 minus high. D low is a chain rule. 2 comes out front. I get x squared plus 2 to the 1 times the derivative of the inside would be 2x. All over low squared, and so I have x squared plus 2 squared. When I square that, I'm going to get it to the 4th. Now, we have to clean up the numerator, and I would think, oh man, that means I need to multiply that out. I need to FOIL that out in order to distribute the 8 to it. But do I really?
No.
Because of that single term in the denominator, I can factor an x squared out plus 2 out of the entire numerator and simplify it with the denominator, so I'm not going to have to FOIL that out. So let's do some work here first. X squared plus 2 squared times 8. And I'm just going to clean up this second term here. 8x times 2 is 16 times another 2x. This is minus 32x squared times x squared plus 2. All over x squared plus 2 to the 4th. So now I see I can factor one of the x squared plus 2's from the first term and the only x squared plus 2 from the second term to the front. And I'm going to get x squared plus 2 times what is left here is x squared plus 2 times 8 minus 32x squared all over x squared plus 2 to the 4th, and one of these will simplify, and that's going to become to the 3rd power in the denominator. Okay, so what do I really have in my numerator here? I'm going to distribute this 8x squared plus 16 minus 32x squared all over x squared plus 2 cubed. All right, so if I combine like terms, 8x squared minus 32x squared is negative 24x squared plus 16 over x squared plus 2 cubed. All right, so that's my second derivative. So we're looking for our possible points of inflection. That's why we find it. Those occur when it equals 0 or when it's undefined. Pretty much the same denominator we've been working with the whole time, right? Is it ever going to be undefined? No. So my possible points of inflection, okay, so that's points of inflection question marks. I don't know if they're going to be or not, are going to come from setting the numerator equal to 0. So I'm going to get x squared equals, well, subtract 16 from both sides, divide by negative 24. That's 16 over 24, because the negative by a negative. Simplify that. I divide both by 8. I'm going to get 2/3. And I'm going to take square root.
Wait, don't you have to do?
This gives us x squared is 2/3, which means x equals plus or minus the square root of 2 over 3. Now that's okay. It's not a nice number. It doesn't have to be. We see that all the time in graphing, in when we find maxes, mins, whatever, and we use the graphing calculator to find it for us. We can get irrational numbers. That's fine. But if I'm going to test to the left and the right of it, I kind of need to know what it is in decimal. So if I turn this into a decimal number, I'm going to get plus or minus approximately 0.82. Okay, that's rounded, because this is an irrational number. It goes on forever without repeating. Okay, so let's relist some information here. My first derivative is 8x over x squared plus 2 squared. My second derivative is negative 24x squared plus 16 over x squared plus 2 cubed. Our critical numbers only gave us x equals 0, and our possible points of inflection now are x equals plus or minus 0.82. So I'm going to put all of this on a number line. And just to keep track of what I'm testing for, I want to note that this one is the only possible extrema. If I didn't get it from the first derivative, it's not going to be an extrema. So those possible points of inflection are only going to possibly be points of inflection. Now, that doesn't mean this is an extrema. We have to test for it, but it's the only possible one. And then these other two might be points of inflection. So we're going to pick some test points, plug them into the first derivative to figure out if our extrema is a max or a min.
This would be 1 and negative.
I could. It's not what I did on my paper. Okay, I'm not going to for a reason. I'm going to pick in between the points of inflection. Now, technically, if I was only doing the first derivative test, and 0 is my only critical number, I could pick anything to the left and the right of 0. But I'm going to go with negative 1/2 and 1/2 because I can use those for my second derivative as well. Okay, and when I test for the concavity, I'm also going to need negative 1 and 1. But I'm not going to test for everything because I don't want to test all 4 of those points in my first derivative when I know the sign of the first derivative is only changing to the left and the right of 0, maybe. So if we plug negative 1/2 into my first derivative. Now, first of all, let's look at the denominator. Is that denominator ever going to be negative?
No.
No, I got some quantity, and actually that quantity can't ever be negative, but whatever that quantity is, if I square it, it's always going to be positive. So I only care about the sign of the numerator. If I plug a negative 1/2, I'm going to get a negative numerator divided by a positive, so we have negative, this is decreasing. If I plug in the positive 1/2, we're going to get a positive numerator. It's increasing. So we have a minimum at 0. Now, I'm going to have to go back to my original function to find the y value that goes with it. But does anybody happen to remember that we've already seen that point in this problem? That was our intercept, right? So it's going to be 0. But just to remind you what we started with, our function is 2x squared over x squared plus 2. So when we plug 0 in there, we're going to get 0, 0. So our intercept is also our minimum. Okay, then if I'm going to test for concavity, I'm looking to see is it changing to the left and the right of negative 0.82. So now we're plugging into the second derivative. Now I can write my second derivative as, let's see, what do we want to pull out? Let's pull out 8, and then I'll have negative 3x squared plus 2. And I did that just because to find the sign of it is going to be easier if I'm not working with such large numbers. Now in this case, my denominator's cubed, so it could be negative, right? Except for, look at what's on the inside of it.
Yeah,
X squared, I add a number to it, always going to be positive. So I'm only worried about the sign of the numerator again. So if I plug a negative 1 into my numerator, when I square it, I get a positive 1. I've got negative 3 plus 2. That's a negative number. So this is less than 0 over here. Am I concave up or concave down? I am concave down. Now, technically, anywhere in between here is a good place to evaluate. I could even evaluate at 0. But there are certain problems where I'd want to evaluate at all of them, so I'm just going to go evaluate at all of them. But in between negative 0.82 and 0.82, I should not have a change in concavity because they are the only possible places for it to change. So what if I plug in negative 1/2? Well, it'll become a positive 1/4, and negative 3 times positive 1/4, that's negative 3/4 plus 2. That's going to be a positive number, right? So we have a positive over a positive. I am greater than 0 here. I am concave up, so I just found a point of inflection. Same thing's going to happen with positive 1/2 because we're squaring it again, right? So I'm still going to be positive, which is a good thing. We weren't supposed to change concavity in between there. And then if I plug in a 1, I get negative 3 plus 2. Well, that's negative 1, so we're back to less than 0. I am concave down. I found another point of inflection. Okay, so those occur at negative square root of 2/3 something and square root of 2/3 something. Okay, so when I plug these values into my original function, I get y values of 1/8. Okay, so this is a lot of information I'm going to have to put on the sketch of my graph. Okay, so we have information that tells me there are no vertical asymptotes. My domain is all real numbers. We have a horizontal asymptote at y equals 2. We have an intercept, which also is the relative minimum at 0, 0. Then we have points of inflection at, now, in order to put these on the graph, I kind of need to leave them as 0.82 and not square root of 2 over 3. Otherwise, how do I know where to put them in between which tick marks, right? So I've got points of inflection at negative 0.82, 1/8. 1/8 is 0.125, I think. We'll double check when we put it on there. And then I also have to pay attention to the concavity of the things I put on here. Now, all of this pertinent information I need to put on this graph are small numbers. So they're going to fit, which means I can put tick marks. I can actually draw this graph to scale. I don't have any wild y values like 146. But I want my graph to be spaced out enough for me to really see what's going on. So I'm making large tick marks there on my y-axis. Pretty large ones on my x-axis. So the first thing I'm going to put on this graph is that I have this horizontal asymptote, because that is a guide for me to draw the graph. My y values are going to approach that as I go off to positive and negative infinity. Now I also know that I have the point 0, 0. And I have the point negative 0.82, 1/8. Well, we're going to exaggerate it a little bit, but let's say that's about there. And then we have its counterpart. So this is actually going to be symmetric. Okay, but let's see what else we know about this.
It's not going to have a maximum.
It is not going to have a maximum except for it's approaching the horizontal asymptote, but it never hits it. Okay, but in order to draw this, I want to draw the concavity correctly. So at 0, 0, I'm concave up on both sides of that. So on my graph, I want to make sure it looks like it's concave up. Now I haven't quite connected the dots because I want to make sure I know what's going on at those point of inflections as well. So when I look at negative 0.82, I'm concave down to the left, concave up to the right. So here I see the concave up to the right, so I can continue that. that looked good. And then I'm switching to concave down. Now, I didn't quite get it perfect yet, but I'm going to continue to extend it. Now, our number line here tells us about every point on this graph where behavior changes. So nothing changes to the left of negative 0.82. So as I continue to the left, I continue to be concave down, and I'm going to approach that horizontal asymptote. I don't know exactly how rapidly I'm going to approach it, and that's why it's a sketch, but that's pretty much what my graph's doing. On the right, I go from being concave up to concave down at that point of inflection. And I'm going to continue up and approach that horizontal asymptote. Now, because I'm not perfect, because my 0.82s are approximations, I want to label the points on my graph that were important information so that in case I didn't draw it perfectly, it's okay because it's labeled. So I have 0, 0 here as the min, and I don't have to label that one because I got it right. I went through the origin. But not all of them are going to have maxes and mins going through a tick mark. So it's good practice to label your maxes and mins. And then I'm going to label my points of inflection. And I don't need you to tell me it's a point of inflection because if you've drawn it correctly, I see the change in concavity in the graph, but I need to know what it is. And in this case, whether I do it as a decimal or whether I do it as square root of 2 over 3, I'm going to know what you mean if you've done it accurately. So labeling it either way would be fine. And then just in case,
With no fraction. Like 1 over 8. Right?
no, I left it as 1 over 8.
Okay.
I could also put that one as decimal. And just in case it's not clear, I'm going to put that my horizontal asymptote is at y equals 2. Because again, on a different problem, that asymptote could be at y equals 24. And in that case, I'm not going to have all the tick marks to put it on there perfectly because it's a sketch. And that would be all the information you would need to tell me about this graph. I can see the concavity if you've drawn it correctly. I can see the minimum value is a minimum. The other points that are approximations are labeled, and that was what I need to see.